Good day guys, welcome back to Wiki Science YouTube channel. In this video, I'll be putting you guys through on how to determine the half-life of the radioactive material as well as the decay constants, and we also have the percentage of disintegration as well as talking about the remaining number of atoms of the radioactive material. I implore you guys to pay absolute attention to this video because it's really going to be helpful for you guys in the course of your exam. If you've been with us before, I really appreciate you guys for your support, but if you are new to this video, ensure you try as much as possible to subscribe. Let's get started. What is half-life? Half-life is a time taken for half of the atom of a radioactive material to disintegrate. Meaning that if I have 1,000 atoms, the time taken for this atom to be reduced to half of this 1,000 will be 500 atoms. So in this case, what has taken place, the time taken for this to occur is called the half-life. As well as the time taken for this particular 500 to disintegrate to 250. Half of 500 will be 250. In this case now, we call this as well the half-life. Okay, shortly, let me give you a formula which you'll be dealing with in order to calculate half-life that relates half-life to decay constant. Half-life of a radioactive material is equal to 0.693 over the decay constant. 0.693 over the decay constant. In another way round, you can as well determine that your decay constant is equal to 0.693 over your half-life. So this is the formula to determine the half-life of a radioactive material. But sometimes they might not ask you to calculate the half-life, nor they ask you to calculate the decay constant. What they ask you to determine, you will be asked to determine the number of disintegration per second or per atom. Okay, before we go into that, I want you guys to know that this ladder that we have here represents decay constant. Why this T subscript half is equal to half-life. So when you are dealing with a case whereby they ask you to determine the number of disintegration per unit time, you have it to be number of disintegration. We use the n over the t to represent that, and that is equal to what we refer to as 0.693 over the half-life, and you have it here to be close bracket the initial number of atoms. So where we have that the n over the t is the number of disintegration per unit time, and we as well have it that your n naught is the initial number of atom, and you have your t half to remain your half-life. So in this case now, you can be asked to determine the number of disintegration per unit time. This is the relationship I expect you guys to be using. I will take reference question on this aspect. For instance, this question states that a radioactive isotope has a decay constant of 10 raised to power minus 5 per second. Calculate the half-life. I've told you guys that in order to calculate half-life, we say T half is equal to 0.693 over the decay constant. And we've been told that the decay constant is 10 raised to power. We have it to be 10 raised to power minus 5. When we take this 10 raised to power minus 5 up, it becomes 10 raised to power 5. Then we have to be 0.693 times 10 raised to power 5. So our half-life equals 6.93 times 10 raised to power 4 seconds. So that is our answer. Now I want you to know that the decay constant also determines the unit which you have your half-life. And most time your half-life is usually in seconds, minutes, it can be in days, depending on the kind of unit which you have that you are dealing with in the question. We'll take another question, for instance, again, dealing with the number of disintegration per second. A piece of radioactive material contains 10 raised to power 20 atoms. If the half-life of the material is 20 seconds. The number of disintegration in the first second is dash. So the number of disintegration in the first second is talking about the number of disintegration per unit second, that is per second. And don't forget, from the formula I've given you, number of disintegration per unit time is equal to 0.693 over the half-life in bracket. What we have here now is the number of atoms, the total number of atoms. And from here, we have it to be 0.693 over the half-life which you have been given here. The half-life is said to be 20. So over 20, and that is in bracket the number of atoms. The total number of atoms is said to be 10 raised to power 20. In this case now, I'll have it to be, that is, when I get from here, I have it to be 10 raised to power 19, and here 0. So from here, 2 in 0 is 0, 2 in 6 is 3, 2 in 9 is 4, and 2 in 13 is said to be 6. We have remainder 1, that is 6, 5. That is times 10 raised to power 19. And from here, I'll have that the number of disintegration per unit time is equal to 3.47 times 10 raised to power 18 atoms. So it means that in every 1 second, this is the total number of disintegration that we are having. We will move to another factor that which they can ask to determine, like the fraction of the remaining atom after disintegration, and as well the percentage of disintegration. We can also look at the remaining number of atoms after disintegration. So let's quickly look at this now. Your fraction of dissociation is equal to 1 over 2 raised to power Tn over T half. What this Tn stands for is the total time taken for disintegration, and what your T half means as usual is the half-life. So when you are asked to calculate the fraction of disintegration, you state that your fraction of disintegration is equal to 1 over T raised to power Tn divided by T half, T subscript half, where Tn is your total time taken for disintegration and T half is your half-life. In other way round, they can ask you to determine the remaining number of atoms. The remaining number of atoms here after disintegration is equal to N0, which is the total number of atoms before disintegration, divided by 2 raised to power T n divided by T half, where you have it already that your Tn is the total time taken for disintegration and your T half is the half-life. But here now your N0 is set to be, the N0 here is set to be total number of atom before disintegration. And you can have that your R is the remaining number of atom after disintegration. Remaining number of atom after disintegration. Okay, for the last aspect, they might tend to include the percentage that disintegrated instead of giving you the fraction. When you come across percentage that disintegrated, you just state that your percentage of disintegration 1 minus percentage of disintegration is also equal to 1 over 2 raised to power Tn divided by half-life. Don't forget, this T subscript half is representing half-life. So this percentage D is the percentage that disintegrated. This is the percentage of the atom that disintegrated. With respect to your question you are answering, you can determine which of the formula to use. So let's take reference questions with respect to each of this formula that I've given you here. For instance, in this question we have that a radioactive element has a half-life of 4 days. The fraction that has disintegrated in 16 days is dash. So here, the half-life is said to be 4 days, and the total number of days for disintegration, which is Tn, is said to be 16 days. Now what they ask us to determine is the fraction that disintegrated, and I've told you that fraction of disintegration is equal to 1/2 raised to power Tn divided by T half. So here we have it to be 1/2 raised to power Tn is 16 and T half, which is your half-life, is 4. So we have it that fraction of disintegration is 1/4 divided by 16 is 4. So we have to be 2 raised to power 4. And then we have that our fraction of disintegration will be 1/2 raised to power 4 is 1/16. So 1/16 is our answer. Where we have it that 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So this is our answer. You don't need to stress yourself, just read the formula and get it done. Let's take another reference question with respect to what we've learned so far. Here is another question which states that a piece of radioactive material contains 1000 atoms. If its half-life is 20 seconds, the time taken for 125 atoms to remain is dash. The remaining atom from the question is 125. The half-life is said to be 20, and the number of atoms before disintegration was said to be 1000. So here we have that your R is equal to N0 over 2 raised to power Tn over T half-life. What they've asked us to calculate is the time taken for it to disintegrate to this 125, which is the total time taken. So here we have that the remaining number of atoms is 125. Your total number of atoms before disintegration is said to be 1000, is equal to, here what you have will be 2 raised to power, the total time is said to be Tn, which you do not know. The half-life is said to be 20. So therefore we can say that 2 raised to power Tn over 20 equals 1000 over 125. And from here we can have it that 2 raised to power Tn divided by 20 is equal to 8. So here we have 2 raised to power Tn over 20 equals 2 raised to power 3. We can take this to be equal base. And if this is equal base, T subscript n over 20 is equal to 3. And from here we have that Tn is equal to 3 times 20, and that is 60 seconds. So our answer is 60 seconds. Let's look at this last question, which states that if 75% of a radioactive material disintegrated in 5 minutes, calculate the half-life. Time taken for disintegration is said to be 5 minutes, and that is our Tn. The half-life is what we are looking for. And here we have the percentage of disintegration is said to be 75%, and that 75% is the same thing as 0.75. So using the formula that 1 minus percentage of disintegration is equal to 1/2 raised to power Tn divided by T half. So from here we have it that 1 minus, what you have here is 0.75 is equal to 1/2 raised to power 5 minutes over what you have, which is half-life, and that's what we're looking for. So from here we have to be 0.25 is equal to 1/2 raised to power 5 divided by your half-life. So from this particular expression here, 0.75 here, we can have it now that 2 raised to power 5 divided by your half-life is equal to 1/0.25. That's when you interchange this. In this case now we have to be 2 raised to power 5 divided by our half-life is equal to, what we have here now is 4. Since you have it to be 4, 2 raised to power 5 divided by your half-life is equal to 2 raised to power 2. Here we also have equal base. And since we have equal base, you can as well say that your 5 over your half-life is equal to 2, meaning that your half-life is equal to 5/2. So here our half-life is said to be 2.5 minutes. So if it is 2.5 minutes, it means that we have it to be 2 minutes 30 seconds. 2 minutes 30 seconds. So that will be the answer. 2 minutes 30 seconds. So that will be our answer. We've come to the end of this video. If this video has been really helpful in order to calculate half-life, the decay constant, the percentage of disintegration, as well as the remaining number of atoms, please ensure you share this video with your friend. We'll be having other questions which you can do it on the screen shown to you. Solve this question and ensure you also subscribe. Thank you very much.